3.4 Parallel and perpendicular lines. We are going to relate parallel and perpendicular lines. If you remember, our definition of perpendicular is a right angle. If lines are perpendicular, you have 4 right angles. We are going to use the relationships of 2 lines to a third line to determine if lines are parallel or perpendicular. Now, as we get going here, you'll see the relationship. This is just an extension of what we did in 3.2 and 3.3 with our 2 lines cut by a transversal, cut by a third line, intersected by a third line. All right, our first theorem here says that if 2 lines are parallel to the same line. Now let's look at what we have. We are told that A is parallel to B, so I mark those, and that line B is parallel to line C. We use our 2 marks, our 1 mark on the first one, 2 marks on the second one, because these are 2 separate ideas. But what do you see here? There's our same line. A is parallel to B, and C is parallel to B. We have 2 lines parallel to the same line. B is the same line. Now, when you're looking at this, hopefully you see what's going to happen here. They are going to be parallel to each other. We can say that A is parallel to C. Line A is parallel to line C. And I enjoy calling this, loosely calling this, the transitive property of parallel lines. Do you see why I like to call this the transitive property of parallel lines? It's like the law of syllogism was transitive property for words. So do you see the transitive-like property here? This is an easy one. You'll be able to do that. Our next one here, no name, so you'll have to write it out, says that in a plane, that's important and we'll see why later, in a plane, if 2 lines are perpendicular to the same line. So let's see what that does for us here. We know that line M is perpendicular to line T, and line N is perpendicular to line T. So we have 2 lines that are perpendicular to the same line. Our same line here is line T. What did I just mark? I just marked a transversal, didn't I? We have 2 lines intersected by a transversal. Do you see what we have here? Do you see corresponding angles? Hopefully you do. So if our 2 lines are perpendicular to the same line, then what are we going to say about these lines? These lines are going to be parallel to each other. We can say that these lines are parallel, so we are going to be able to mark them parallel. And this is like the converse of our corresponding angles postulate. What did the corresponding angles postulate say? It said if corresponding angles are congruent, then our lines are parallel. So we don't have congruent angles here. We sort of do. We'll look at the proof here in a minute and see why. But can you see how this is like our converse of corresponding angles postulate? We have corresponding angles that are congruent. 2 lines cut by a transversal, corresponding angles are congruent, then we can say our lines are parallel. Let's look down here at our proof of this to see what's happening. We are given that line R is perpendicular to line T, and line S is perpendicular to line T. I see two lines cut by a transversal, so I'm going to mark my transversal. Only how do we prove this if our angles aren't congruent? Well, the first thing that we can say is that angle 1 and angle 2 are right angles. How can we say that they're right angles? Well, that's just the definition of perpendicular, right? And then, guess what we get to say? That angle 1 is congruent to angle 2. Now, you might feel like we're skipping a whole bunch of steps. We could say, well, if angle 1 and angle 2 are right angles, then we can say that the measures of the angles are 90 degrees. That's just definition of right angle. And then we can just substitute and say that our measures are equal. Measure of angle 1 equals measure of angle 2. And then by definition of congruence, if your measures are equal, your angles are congruent. But we don't have to do all of those steps because we have already done that in a previous theorem. Think back to chapter 2. Angle 1 and angle 2 are right angles. And what theorem do we have that lets us just jump to this step? All right angles are congruent. Now, isn't that so much better than having to do all three other steps? I told you this is one that you'd like. So I can simply say that angle 1 is congruent to angle 2 because all right angles are congruent. And then these are just corresponding angles here. I can say that line R is parallel to line S by the converse of corresponding angles postulate. Because now I have made these angles congruent. So this is the proof of our theorem that says if two lines are perpendicular to the same line, then they are parallel. Now this one doesn't have a name, so how can we shorten this? Two lines perpendicular. Oh, we should write the word 2 in there. To the same line are parallel. You can shorten it to that. But just think converse of corresponding angles postulate here. And know that this is a special case for perpendicular. All right, how can we use this in problem solving? Well, this is kind of fun. We are told that a carpenter wants to install molding on the sides of a doorway, sides and top of a doorway. So this is just putting in a door jamb. And he cuts the ends of the top pieces and the sides at 45-degree angles. So let's look at our diagram here. We have 45, 45, 45, 45. And I can mark them all congruent because they have equal measures. We want to know, will the side pieces be parallel? So what are we looking at here? Let's draw a picture. We have two side pieces and a top piece. And why did I draw it that way? Because I have two lines intersected by a transversal. And then what do we have? We know that these are going to come out. We're going to have 45 and 45, right? And they're going to come in here, 45 and 45, like that. Are they going to be, that's really messy. I don't like that. Really messy. So we have come in that way, come in that way. This one here is 45 degrees. This one here is 45 degrees. This one here, 45. This one here, 45 degrees. What is that going to do for us? What's 45 plus 45? 90. So each side is perpendicular to the top. If two lines are perpendicular to the same line, then they are parallel. Do you see two lines perpendicular to the same line? We can mark them parallel. So yes, if he uses 45-degree angles, it's all going to be good. All right, you try it. We can keep this. No, we can't. Pause the video and see if you can do the next problem. Okay, did you make it work? What angles do you see? Can you put together a picture frame that uses these pieces and will be parallel? And I'm pretty sure that you saw that 60 and 60 and 60 and 60, and we put our 30s in like this. And yes, we are going to make 90-degree angles, which means they are perpendicular, and 90-degree angles here. So we will not only have perpendicular lines this way, but we will also have perpendicular lines this way. So these will be parallel and these will be parallel. So yes, you can put them together in a way that will make it happen. You could also put them together so that your 60s are together. Wouldn't work at all. All right, let's look at our next theorem. This one has a name. We like it when they have names. This is the perpendicular transversal theorem. Words that we've seen before. We're going to be perpendicular to a transversal. I like it. So in a plane, if a line is perpendicular to one of two parallel lines, so let's look at what is happening here. We know that line N is perpendicular to line L. Okay, and we know that L and M are parallel. Actually, let's do that in green. That's one of our givens here. We know that those lines are parallel, right? Line L is parallel to line M. Then what can we say about this? What do you see here? Take a look at this. I see two parallel lines cut by a transversal. Do you see our transversal? We have two parallel lines cut by a transversal. What are we going to be able to say? Do you see the corresponding angle there? And our corresponding angles are congruent. So if a line N, is perpendicular to one line, one of our parallel lines, that's the important part here, then it is also going to be perpendicular to the other line. This is like the corresponding angles postulate. The corresponding angles postulate said if we have parallel lines cut by a transversal, then corresponding angles are congruent. So the parallel lines is the important part there. And we don't actually have angles with measures so that they can be congruent, but perpendicular is a form of measure, kind of in a way. Right angles eventually can be congruent. Okay, do you see how that one is like the corresponding angles postulate? If you think of these like what we did in 3-2 and 3-3, they will be easier. These are just special cases of your corresponding angle postulate that uses perpendicular lines. All right, our perpendicular transversal theorem says that our lines must be in a plane. Why does this have to happen? Well, let's take a look. If we look at these lines, line AC and BD, and we know that those lines are parallel. And we have this plane up on top here. And then we look at line EC. We know that line EC is perpendicular to line AC. But because line BD is also part of this right side plane, it's a different plane than this ACE plane. So what happens here is line EC is perpendicular to AC, but not BD. Even though these two lines are parallel and line EC is perpendicular to one of them, it is not perpendicular to the other. As a matter of fact, EC and BD are skewed. Remember what skew is? Non-coplanar, they do not intersect, and they are not parallel. Because they are not in the same plane. So our perpendicular transversals theorem only works if everybody is in the same plane. So be careful of that. All right. Let's do some examples with these. Let's look at what we are given. We are told that in a plane, always a good thing, that line C is perpendicular to line B. All right, so we can find line C and line B and mark them perpendicular. Line B is also perpendicular to line D. Oh. Do you see that? Do you see that? What's that going to let us do? This is going to let us make C perpendicular or parallel to D, right? Two perpendicular lines. Two lines perpendicular to the same line. Do you see that? That's our first theorem right there. All right. We haven't even started our proof yet. We don't even know what we want to be able to prove. But I see that as I am marking my given. So I make a little note of it. That's our define explore. And line D is perpendicular to line A. Oh, do you see our corresponding angles here? Do you see our perpendicular transversals theorem? No. Wrong one. It's the same thing we just did. We have two perpendicular lines here. We're going to be able to say A is parallel to B. We've got two lines that are perpendicular. All right, so what are we trying to prove? We are trying to prove that C is perpendicular to A. Oh my goodness. But you're looking here at the diagram, C and A don't even intersect. Oh, but they do. We can extend this. This is a line. It goes on forever. So we want to prove that these two lines are perpendicular as well. So let's look at how we're going to do this. So let's start out here. We have our given. All of this stuff here is given. I'm not going to write it in the interest of space, but know that we have all of our stuff and our given. It's our first step always, right? All right, so we know that C and D are both perpendicular to line B. I am going to separate these out here, C and D and B. And I am just going to look at these three lines. I know perpendicular, perpendicular. So what does that let me say? I see two lines cut by a transversal. I am going to be able to say that line C is parallel to line D because two lines perpendicular to the same line are parallel. Right? C is parallel to D. Do you see that? So we now have those lines are parallel. Now I am going to redraw this again. Let's have more space here. I now have two parallel lines, C and D, and I can mark them parallel. And now I have transversal A. And I know that. So do you see a theorem there? Do you see one of our theorems that we just made? I have two perpendicular lines, two parallel lines, and one of them is perpendicular to another line. I am going to be able to say that line A is perpendicular to line C. Wrong way. By my perpendicular transversal theorem. That was pretty easy. Do you see up above here how it made it so much easier when I redrew what I had so that I could see where I was going? All right, let's look at the last problem here. Pause the video, see if you could do the last problem. Okay, what did you figure out? We want to know if we could also conclude that A is parallel to B. Do we have that information? Well, let's draw another picture here. There's A, line B, and we can just take this last step that we had and we have it either from, this can be either line C or line D. What do we know here? We know that it's perpendicular there and perpendicular there. Can we prove that those are parallel? Yes, we can, because two lines perpendicular to the same line are parallel. And you also could have done this. There's A and B. We just proved that those are perpendicular. So it doesn't matter which one of these you use, we end up with the same reasoning. These, you want to be confused by these, but don't be. Use your define, explore. Think of them as corresponding angles. It's just special cases where your lines are perpendicular instead of being congruent or having angle measures. Okay, and we know that perpendicular means right angle, which means congruent, so they actually are congruent. You'd have to put in the steps. But that's why these theorems work, because this is a special case for perpendicular lines, for right angles. And use your Define Explorer to redraw the pieces, and if you have to, turn your paper so that your pictures match the drawings in your notes. That way you can compare them and see if you've met all of the requirements. I truly believe that you can do these. Just be careful and stop and think about them. And as always, enjoy the homework.